inject three-phase time displaced currents into three-phase space displaced winding, it is going to create a revolving magnetic field. So we said basically three-phase time displaced current injected into three-phase space displaced windings, right? This creates a revolving magnetic field. In fact, although we have looked at the specific case corresponding to three-phase, it's true for any M phase. That is, if I am talking about two-phase or three-phase or n number of phases, generally it will be true. So we are specifically taking a three-phase case. There are two-phase induction motors as well, where we may have only two-phase supply, but two-phase supplies are not displaced from each other by 180 degrees, it is rather by 90 degrees. That's all is the difference. They will be displaced from each other by 90 degrees. The windings will also be displaced from each other by 90 degrees, which means if I have a two-phase induction motor, I will have maybe A and A dash here, whereas I'm going to have the next phase somewhat coming like this. So this is dot and let us say this is cross. I will have this as dot and this as cross. This will be A phase, whereas this will be B phase. And if I try to look at the two currents which are time displaced, this may be one phase and the second phase will be 90 degrees shifted from this. This is how it will be. So we are going to have basically two-phase induction motors as well, but two-phase induction motors are generally meant for a little lower rating. Hardly ever we use it for a regular rotational mechanism with high power rating. We generally use it in some mechanisms which are known as servo mechanism. So two-phase induction motors are generally used in servo mechanisms. The servo mechanisms, yeah. No, this will not have oscillation in the speed because both the powers together ultimately is going to give rise to again a constant value of torque and constant value of power. That is one thing. And second thing is also this will also create a revolving magnetic field which will work at the same speed as that of the frequency of the supply. So that magnetic field is the one which is the root cause for the induction of the torque ultimately. So it will be a steady value basically, because the flux value is a constant value because of which everything ultimately becomes steady, right? So this is used in something called servo mechanism. Servo mechanism is mainly for position control. What we mean by position control, for example, if you have an air conditioning unit, there are vanes. You may like to keep the vanes completely open. You may like to partially close it depending upon the temperature. Or for example, let's say there is a telescope. You want to observe a particular planet or whatever. Okay? And then you want to probably change the position of the complete arm by certain angle so that you observe something which is very close to that. So how much is the angular movement you want to have? You might have some kind of a closed loop control system. You will say whether you have reached this much of displacement or not. So you might like to move only a little bit. It is like a robotic arm movement. So you might like to have only a very, very short movement. It is not for continuous rotation. It is only for a shorter span of movement. So those mechanisms are generally known as position control mechanism. We would like to control the position by adjusting the position of a lens, position of probably a robotic arm, pick and place kind of robo. In those cases, you might require this kind of a mechanism. So this may not be of larger rating, but this will be specifically for a smaller rating, but still it might require a rotation for a short while. So in those cases, servo motors are used, and two-phase servo motor, two-phase induction motor is very commonly used as a servo motor. One more point I have to mention before we move on further is, we told that the induction motor can be wound for 2-pole, 4-pole, 8-pole and so on. So if it is, for example, 4-pole, then what I will have is, if this is my stator, I will have basically, this is A and this will be A dash. And this will be A1, which is also corresponding to A phase, and this will be A1 dash. So this, please remember, I'm going to have everything doubled. A phase winding was only A and A dash earlier. Now I'm going to have 2 positive carrying conductors, 2 negative carrying conductors for A phase. Similarly, I'll have to have for B phase also 2 positive and 2 negative. So which means, rather than displacing from A, B was displaced earlier by 120 degrees. Instead of that, now it will be displaced only by 60 degrees. I will divide everything into by 2 basically. So this will become B and this will become, again I have to draw here, B dash. And similarly, I have to have one more here and one more here. Are you getting my point? So I will have now B1 and B1 dash. Please note, the more the number of poles, the more will be the conductors that are carrying positive current, the more will be the conductors that are carrying negative current. So many conductors will be, making up for one particular phase. So, if you actually look at it, although I am having, if I look at the displacement between this to this, it is only 90 degrees. But that is going to be equivalent to the electrical displacement of 180 degrees. Because electrically, one is positive, the other one is negative. So, if I look at the electrical displacement, it will be 180 degrees. Whereas, if I look at actually the mechanical displacement, it is only 90 degrees. So this leads us to the discussion on mechanical degrees and electrical degrees, or mechanical radians and electrical radians. So if I try to look at the electrical degrees, that essentially depend upon how I have wound the winding, for how many poles I have wound the winding, and from where to where it is going from positive to negative. So in this particular case, I have wound it for 4 poles. So this is a 4-pole winding. So if it is a 4-pole winding, I would say 90 degrees of mechanical is equivalent to 180 degrees of electrical. So I should say electrical degrees divided by the number of pole pairs is equal to the mechanical degrees. Yeah. 60 degrees. Instead of 120, this should be 60. I have not shown it probably as 60, but what I am trying to say is, this is the center. If I say this is at 0 degree, this should be at 60 degrees. Instead of 120 degrees, now I will put it at 60 degrees. From here another 60 degrees, just a second. From here another 60 degrees, I will put C and so on. Yeah. Huh. See, it would have cancelled out each other. That's the only reason why in 2-phase it is always 90 degree. That is the only exception. If I look at 3-phase, it is 360 divided by 3. If it is 4-phase, it is 360 divided by 4. 2-phase is the only exception. Right? Maybe you can try this exercise. Try to give 180 degrees and see whether you will get a revolving magnetic field at all. You can do the same derivation, what we did in the morning. Right? And I don't think we will get it. It will cancel out. That's what I think. So, that's the reason why the 2-phase is always having 90 degree, basically. Right? Now, if I am going to have, this angle has to be 60. Because previously when I was doing between A and B, it was 120 degrees. You remember? Now everything is halved. Everything is halved. Previously between A and A dash it was 180 degrees. Now between A and A dash it is 90 degrees. So what I am trying to do is compress one cycle of the electrical oscillation into half rotation. I am trying to compress one complete cycle of oscillation into half the rotation. Previously what happened was one period of electrical oscillation was also equal to one period of the mechanical rotation. Now I have just made it half because I have put 4 pole instead of 2 pole. This is 3 phase. 3 phase, I have only shown 2. The third one I have to show very clearly. If I have to put the third one, I have to again delay it by 60 degrees from here. I am only worried that I will not be able to draw it very accurately. It will be a problem. That is the only thing. So I am going to get C here. Right? And so on and so forth. So we are actually looking at multiple poles coming into picture, in which case I am going to have the mechanical speed decreasing. So the mechanical speed will decrease because it is actually divided by the number of pole pairs. I said originally that omega electrical will be equal to the rotational speed of the field, magnetic field. This we could say only because it was having only 2 poles or 1 pole pair. So this is true only if P, the number of pole pairs. So this is only if the number of pole pairs is equal to 1. If the number of pole pairs is increasing more than 1, then I have to divide whatever I am getting as the mechanical velocity, that will be electrical velocity, divided by the number of pole pairs. So if I say that it is actually 50 hertz, right? If I say it's a 50 hertz supply, which is the normal supply what we use. So if I say that F is equal to 50 hertz, then I'm going to get for 2 poles, I'm going to get the rotational speed also as 50 revolutions per second. Right? Because both of them are exactly the same. 50 times oscillations correspond to 50 revolutions. Right? So this is 50 revolutions per second, or I can say 50 multiplied by 60, which is 3000 RPM, revolutions per minute. So if I have 2 poles in an induction motor, you should be able to tell that the synchronous speed is 3000 RPM. Even if I wake you up in the middle of the sleep, you guys should be able to say 3000 RPM is the synchronous speed as long as I run it in India, because it is 50 hertz, right? So if I have instead, so let me write pole pairs and synchronous speed for the frequency. So if I say frequency remains constant at 50 hertz, if I have 1 pole pair, I am going to get 3000 RPM. If I have 2 pole pairs, it will be 1500 RPM for 50 hertz itself. If it is 3 pole pairs, please understand it has to be in a pair. I can't have, odd number. So if there are 3 pole pairs, I am going to have how much? 1000. And so on and so forth. All the frequencies correspond to 50 hertz. Is this clear? So, yes. Pole pair is, if I am going to have, let us say, a north pole and south pole, which is an imaginary pole. It is not really the actual pole. It is an imaginary pole. So it is as though I am rotating this. So this is 1 pole pair. If rather than that, so previously I had A here and A dash here. Right? So I was creating only 1 north and 1 south. Rather than that, if I am going to have 1 A here, 1 A dash here, 1 more A1 here and 1 more A1 dash here. Right? Then I am going to have actually the poles as though This is a north pole, this is a south pole, this is a north pole, and this is a south pole. So that is equivalent to 4 poles being rotated. Right? That's what it is. So, between this north pole and south pole, although it is 90-degree displacement, I am actually having 180-degree traversal as far as the electrical current is concerned. So, essentially the traversal of the electrical degrees is being divided by 2 when actually I come to the mechanical degrees. This is what I am trying to emphasize, right? So, depending upon how many poles, for how many poles you have wound the induction motor stator, correspondingly our synchronous speed is going to change. And according to the frequency as well, but the frequency invariably happens to be 50 Hertz. So, you are going to have basically the number of pole pairs which is going to decide the synchronous speed. If you have understood this, now we will go ahead and look at the principle of operation of the induction motor. Yes. Yes, yes, yes. If I have A and A dash, A dash, A1 dash, it is a 4 pole. It is for 4 pole. If I rather say A dash, A1 dash, A2 dash, then there will be 6 poles. In which case, I have to rather look at 60 degrees equivalent to 180 degrees. You got my point. 60 degrees will be in mechanical, 180 degrees will be corresponding to electrical. That's all. So, the more the number of poles, 4 poles or 2 pole pairs. Either way is fine. Either way is fine. Right? Many books write it in terms of pole pair. Yes. Yeah? Yes, very much. Servo motor is one of the mechanisms which are used in position control. Stepper motor can also be very well used. Only thing is, servo motor can give better torque than stepper motor. Stepper motor is you just give a pulse, it creates a movement. So, the torque capability of the stepper motor is generally limited. Whereas, in the case of servo motor, it can give continuous torque also if it is needed to be given that way. That's not a problem. Pitch of the stepper motor is fixed depending upon how you have designed. Yes. Yeah. How you have designed it. Okay. So, let us, yes. See, if I am saying that from here to here, to come from here to here, actually one complete oscillation takes place in the electrical cycle. From this point to this point to come, it is actually taking place in one complete electrical oscillation. One complete, rather half the electrical oscillation, because this is A and this is A dash, half the electrical oscillation. Half the electrical oscillation corresponds to, let's say, 10 millisecond in a 50 Hertz cycle. So, in 10 millisecond, my revolving magnetic field would have moved only from here to here. Nothing more than that. But if it had been a 2-pole configuration only, then it would have moved from all the way from here to here. So, the way it is moving is from the north to south or from the positive to negative. So, when it is moving from the positive to negative, that corresponds to half the cycle time. So, that is the reason the more the number of poles, the angle traversed keeps on decreasing mechanically. That's the reason. Got it? So, in general, if I wind it for a larger number of poles, I am going to see that generally the speed is going to decrease further and further. As a converse, you may understand it better when we talk about synchronous machines later. I am very sure, maybe I can just make a passing mention. If I have the north pole, south pole like this, maybe in a synchronous machine, imagine This A is going to face first north pole. This is going to face north pole. Then within 90 degrees it is going to face south pole. Again it is going to face north pole, and after another 90 degrees it is going to face south pole. Now what happens as far as the induced EMF is concerned? The induced EMF will become double the original frequency. If it had been only one north pole and one south pole, A would have gotten induced EMF corresponding to north pole. After 180 degrees only it will get an induced EMF corresponding to south pole. So it is exactly matching with whatever was the mechanical rotation. But if I have four poles, it will face north pole at 0 degree. It will face south pole at 90 degrees itself. But by then electrically it has completely reversed. Are you getting my point? So electrical rotation in this electrical reversal has taken place even before it has traversed the complete 180 degrees as far as mechanical is concerned. So that is the way it works. The number of poles increase, then correspondingly the mechanical rotational speed is going to decrease. Right. Now let us try to take a look at the principle of operation of induction motor. I am going to assume that the rotor is short circuited. If it is a cage rotor, it is already short circuited. If it is not a cage rotor, if it is a slip ring rotor, externally I have brought out 3 terminals. Those 3 terminals have to be short circuited. If it is not short circuited, the induction motor will not start rotation. I need to short circuit it. If I need to short circuit it, why bring it out? That is a question mark you may have. I might like to modify the characteristics at a later point. So I reserve the rights to modify the characteristics. That's all it means. So unless I short circuit the induction motor's rotor terminals, the induction motor will not start rotating. Let's see why. I have the stator. Let me show stator per phase one winding as a simple transformer winding. There is nothing much other than that. Okay. And let's say the rotor winding, again I am showing it as a simple transformer winding secondary. I am not even worried about the turns ratio right now. Okay. So this is per phase induction motor winding. That's what I am drawing. Right? This is equivalent to primary, which is the stator, and this is equivalent to secondary, which is the rotor. Okay? Now, I told you that it has to be short circuited, so I am short circuiting it simply. Right? I have applied 3-phase currents to all the 3 phases of this induction motor's stator winding. So I have just connected a voltage source and I have applied the current. So the current drawn should be actually enormously high. We talked about this. In the transformer, if I short circuit it, I will have huge current being drawn if I am going to actually, not include any load. Simply short circuit it. That's it. So in that case, I am going to have a huge current drawn. No wonder induction motor normally draws a very large current during starting. Whether I like it or not, I would see that induction motors draw a very, very large current during starting because it is as good as a short circuited transformer. Only saving grace is, in the transformer, I don't have any air gap between the primary and secondary. I try to minimize the air gap. I put all sorts of things, right? Sandwiched coil or concentric coils. I try to do whatever I can to reduce the air gap so that the magnetizing current drawn is minimal. Here I can't do that because the rotor has to rotate. So I need to provide the air gap. So that air gap serves as a blessing in disguise. That air gap actually will increase the reluctance. Because the increase of reluctance, it will draw definitely some current, agreed, but the leakage is also more. You remember the equivalent circuit of the transformer where actually we drew that this is R1, this is X1. X1 was leakage and I had R2 and x2 was leakage, clearly. And I had the entire thing connected. I'm not even worried about the parallel parameters. I have short circuited. So I'm not really unduly worried about it. So I am going to apply V1 here. This is what we wrote as the transformer equivalent circuit, of course R2 dash, X2 dash. Fine. Now X1 and X2 dash are quite large as compared to what I would have in a transformer, because the leakage is definitely more in the case of an induction motor because of the fact that I have an air gap. So this is going to serve as the limiting factor of the starting current. If I had done the same short circuiting in a transformer, it will be 20 to 25 times the full load current, whereas in an induction motor it is about 6 to 8 times, which is still tolerable. It's not as high as 20 to 25 times the full load current like what you see in a transformer. In the case of induction motor, it may be 6 to 8 times, which is still okay, not too bad. Fine. So now what is going to happen is, this is going to definitely induce an EMF. The moment I initially apply a voltage, that is going to create a revolving flux. The revolving flux is created in the air gap, and the rotor is right now stationary. The rotor coils act like the secondary of a transformer. They get induced EMF. It is already short circuited, so it will also carry a current. So unless rotor current flows, I'm not going to have any further action. Now rotor current is flowing because I have short circuited. This is a motor, no generator. Electrical load you are talking about. I didn't say starting load is 0. I said that I will short circuit the secondary. Induction motor is short circuited if you look at the squirrel cage. You can't remove the short circuit. Even in the case of a slip ring induction motor, unless you close the rotor circuit, the induction motor action itself will not take place as we would see just now. You will have secondary induced EMF in a transformer. The same way in the rotor there is an induced EMF. The moment there is an induced EMF, because the rotor is short circuited, there will be a rotor current. The moment there is a rotor current, the rotor currents are not going to keep quiet. They are also three-phase currents after all. And it is a space distributed winding if I am talking about a slip ring rotor. Even if it is a cage rotor, the currents will distribute crisscross, but ultimately it is a three-phase current in a distributed winding. So it is going to create another revolving magnetic field. So there is a revolving magnetic field created by the stator winding current. There is a revolving magnetic field created by the rotor current, which is an induced current. I didn't supply that current. It was because of induction. Now, these two currents are going to interact. These two fluxes are going to interact. When they interact, they will try to align themselves with each other. If the north pole and south pole of the stator flux is in particular direction, the south pole and north pole of the rotor will try to align itself with those north pole and south pole. So in the process, the rotor is going to develop a torque. The motor is going to develop a torque. For the alignment purposes, it will develop a torque. The torque will be in which direction? That is the next question we have to ask ourselves. Lenz's law comes in handy. So Lenz's law would say that the torque generated would oppose its own root cause. What is the root cause? Rotor current. And why was the rotor current actually flowing? Because there was a rotor induced EMF. Why was there a rotor induced EMF? Because there was a revolving magnetic field. It is a flux which is changing, right? North pole and south pole are continuously rotating. If the rotor had not been stationary, if that had also rotated in the same direction as that of the revolving magnetic field, in the same speed, it would have seen a constant magnetic field, isn't it? So the torque would have a tendency to rotate the rotor in the same direction as that of the revolving magnetic field and try to push it towards the synchronous speed. Go and lock up at the synchronous speed. That's what it will try to push it. Let's say it really succeeds and it reaches synchronous speed. The moment it reaches synchronous speed, the rotor reaches synchronous speed, the rotor conductors would see a stationary magnetic field. There is no rate of change of flux. There is no rotor current. There is no rotor flux. There is no interaction. There is no torque. Then the speed will fall. So this will take place until a beautiful balance happens in such a way that the frictional torque or whatever is overcome. If I don't have any load on the rotor shaft, the frictional torque will be overcome with a small torque developed by a small current flowing, by a small induced EMF, which will come in handy if there is a small relative velocity. So what happens is it starts basically from standstill condition. Please again, I am trying to repeat the whole thing. The rotor was at standstill condition. It was as good as a transformer. Nothing better than that. And there is a revolving magnetic field already set up. Because there is a revolving magnetic field, I am going to see that continuously the north pole and south pole are rotating at a very, very fast rate. That's how it is. I am talking about two-pole machine. I don't want to go into multiple poles. Fine. So in a two-pole machine, this is going to continuously rotate. And I have the rotor conductors sitting here, simply. Right? These are the rotor conductors. The rotor conductors are looking at this particular revolving magnetic field. It is definitely seeing a rate of change. So there will be an induced EMF. d phi by dt is there. There will be an induced EMF in the rotor. That induced EMF causes a rotor current because I have short circuited the rotor. If I don't short circuit the rotor, there will not be any current in the rotor, there will not be any flux in the rotor, there will not be any interaction, there will not be any torque production, the motor will not rotate. You can't call it a motor anymore. It is like a transformer, open circuited transformer. Nothing more than that. So I have to short circuit the rotor, otherwise it will not work. So I'm going to have a rotor current because of the induction. That rotor current is going to cause again a three-phase currents flowing through the conductors in space distributed winding of the rotor will cause another revolving field to be set up. That revolving field will try to interact with the stator created magnetic field, and that is going to produce a torque in the process of aligning with each other. That torque essentially will oppose whatever is the root cause for the torque production. What was the root cause? The root cause was the induced EMF and induced current in the rotor. The induced EMF would not have taken place, or it would have been zero, if the rotor also had rotated at the same speed. Then it would be seeing a stationary magnetic field. Right? If both of them are running at the same speed, there is no way it would see any change in the magnetic field. So in that case, there will be induced EMF which will be zero, there will be no current, there will be no flux, there will be no torque. So the root cause has to be opposed. For opposing the root cause, it starts rotating in the same direction as that of the revolving magnetic field. Right? Now, once the rotor picks up speed, it will go further and further until it reaches almost synchronous speed. When it reaches synchronous speed, the entire operation will cease to exist. It will stop because you are not going to have any more induced EMF, you are not going to have any more induced current, you are not going to have any more rotor flux. All that completely disappears. If it disappears, there is no torque. If there is no torque, the rotation will automatically try to come down. The velocity will come down. The moment the speed comes down from the synchronous speed, again you have induced EMF currents and torque and everything. So induction motor can run only at a speed which is slightly less than synchronous speed. It can never ever run at a speed of synchronous velocity, or it cannot run above synchronous speed. The rotor currents will cease to exist, the rotor flux will cease to exist at that moment, because of which the torque will also cease to exist. Because the torque ceases to exist, it will have to fall down. There is no other way. And the moment it falls down even slightly, you will see that again the rotor current reappears, rotor flux reappears, torque is produced, and there this delicate balance exists between the torque produced and the frictional torque requirement. That is where the motor will settle down. That is the reason why when the motor is running on no load and I suddenly put a load on the motor, let's say I hold probably my shaft of the induction motor, then what will happen? Immediately you will see that it will require more torque. If there is a requirement of more torque, it will need more rotor current. If it needs more rotor current, the speed will decrease, because of which the relative velocity will increase. That relative velocity will induce a larger EMF. Because of larger EMF, there will be a larger current and there will be a balance. That's what happens every time you load an induction motor, right? We'll talk about loading mechanism and so on and so forth further. So I hope qualitatively you have understood how the induction motor runs, how it picks up speed. So if you have understood this, now we will go to the mathematical formulation, right? So if I look at the mathematical formulation, we are going to look at the three-phase induction motor on a per phase basis. We are not going to look at it for all the three phases. So whatever we calculate for one phase, multiply it by 3. That's what we are going to do, right? So let me first of all draw the equivalent circuit of an induction motor under standstill condition, when it is not moving at all. So that is as good as a transformer. So all of us know exactly how the transformer equivalent circuit is drawn. So I can simply say this is R1, this is X1, and here is my magnetizing reactance or the actual coil, and I'm going to have this as the secondary, and I'm going to have R2 and X2. That's it, right? And what I am applying here is V1 per phase, right? I have to short circuit, definitely. I am first starting off with open circuit, and I know for sure that it would have been V2 at the terminal, because hardly any current flows. In the primary also very limited current, hopefully. So I'm going to have V2 as the induced EMF. I'm not unduly bothered about that, because I'm going to anyway, as he correctly pointed out, I have to short circuit. So I have short circuited it. Yes. It is iron core. Core is still iron. There is air gap, agreed. But there is a huge amount of iron involved in induction motor. The rotor core as well as stator core are made up of iron. There is a small air gap, and you will make the air gap as thin as possible in an induction motor. As thin as it could be. Mechanically, whatever is permissible. Right? So it will be only a few mm, even in a very big induction motor. We'll try to minimize the air gap as much as possible. Why? We will look at it again. Right? So we are going to generally have very thin air gap. This clearly indicates the iron core corresponding to stator as well as rotor. There is iron core. Of course, no machine will work without ferromagnetic material. That's the reason we started off with magnetic circuits. Right? And that's why we went into transformer, because transformer and induction motor resemble each other quite well. That's the reason. Right. Now what is going to happen is, of course, I have to include the iron loss component, and the magnetizing reactance as well. That also I have shown now. So this is going to be Xm and this is going to be Rc. Both will be there. I can't help it. These will be there, definitely. So this is the equivalent circuit of the induction motor when I was having basically that in standstill condition. It is not still, it has not started moving as yet, right? Please note that the Xm value in a transformer is generally really large because it consists primarily of only the iron path. There is nothing else. So Xm is N square by R, right? That is N square by R is the inductance, Lm. Lm will be N square by R, where N is the number of turns, divided by R is the reluctance. The reluctance happens to be really small in a transformer, because of which this Xm value is generally very large. Whereas in the case of an induction motor, the reluctance is somewhat larger because I have an intervening air gap between the primary and secondary or stator and rotor winding. The coupling is tight, but not as tight as what I would like it to be, or not as tight as what it happens to be in a transformer. So I will have Xm value to be somewhat smaller as compared to an induction, a transformer. If I look at the transformer, if I say it is like 1000 ohms, this may be like 800 ohms or 700 ohms or even less. That's how it is going to be. Xm value will be smaller. Now I'm going to have actually this EMF, what is induced is E2, and I'm going to have E2 by E1 will be equal to N2 by N1, which is the turns ratio. But this is true under standstill condition. Right? And all of you know the equation for E1 and E2 also clearly. So I'm going to have E1 equal to 4.44 F5 into number of turns N1, and similarly E2 is going to be 4.44 into F5 into number of turns N2, assuming that the same flux links both of them. I have neglected leakage. This is what is the truth. Now, slowly, yes. See, equivalent calculations exist. Basically, what we will be looking at is for what current rating I have designed. From the current rating of the secondary side to the primary side, we look at both of them, rated currents, and then arrive at the number of turns ratio. So we design it corresponding to your current and place the number of rotor bars correspondingly, and then we calculate the number of turns correspondingly. So it is basically a pretty involved design as far as the squirrel cage is concerned, although it looks very simple. But the turns ratio in squirrel cage is not a straightforward one. It is a very straightforward one in the slip ring rotor. It's pretty simple. Whereas in the squirrel cage, I have to calculate the equivalence in terms of currents and torque and everything. From the torque, I will decide what is the current. From the current, I'll decide what is ultimately the turns ratio. Right? From the primary current to the secondary current. That is how we do it normally. We are talking about basically per phase. Per phase, how many ever turns I have got. Per phase, how many ever turns I have got. If I am talking about flux as flux per pole, then I will also have N1 as the number of turns per phase per pole. So depending upon how I am, if I am connecting all of them in series or parallel, those things also matter. Sometimes I may still connect some of the windings in parallel or series, depending upon whether I want a high torque machine or high speed machine, high power machine. Depending upon my ratings, I might connect all the windings in series or parallel. Similar to lap and wave, what we talked about in the case of DC machine. Total number of turns. I am taking the flux to be total flux that is existing in the air gap. That's the reason. pole square. Yeah, if I am talking about N1 also, number of turns per pole. Yes. Okay. So, now I am going to now allow the rotor to rotate. Until now I didn't even allow it to rotate. I was holding the shaft tightly. It is just, trying to rotate. It has not rotated. Now I am just taking off my hand. It has started rotating. Once it starts rotating, I told you that omega r is, that is the rotor velocity is omega r. So the rotor velocity is going to be less than omega s, or the synchronous speed. Right? So we introduce one important term which we use repeatedly in induction motor called slip. Slip is defined as whatever is the difference between the revolving magnetic field speed and the rotor velocity. So I am going to say slip is equal to omega s minus omega r, but generally it is expressed with respect to omega s, because omega s is a fixed quantity for a given frequency for a given number of poles. Okay? And I can express it as percentage slip, in which case I will say multiplied by 100. Right? When the machine started, or it was just in standstill condition, the frequency induced in the rotor circuit is same as that of the stator circuit frequency, because it is like a transformer. The rate of change of flux is similar. Exactly. But the moment the rotor starts rotating, the relative velocity is going to decline. Originally the relative velocity, if I say that the revolving magnetic field was rotating at 3000 rpm, the rotor was at standstill condition. I was having 3000 rpm as the relative velocity between the rotor and the revolving magnetic field. Now the rotor has picked up speed slowly. Maybe it has come to 2000 rpm. So this is at 2000 rpm, revolving magnetic field is at 3000 rpm, the relative velocity is only 1000. So obviously the rate of change of the magnetic field that the rotor conductors is going to visualize will also decline. Originally it was looking at the rate of change at the rate of 3000 rpm. Now the rate of change will correspond to only 1000 rpm. So I will have clearly the induced EMF in the rotor, that frequency will depend upon the relative velocity. Originally the relative velocity was corresponding to F1, if I may call the stator frequency as F1. Now if the relative velocity has declined, this will correspond to S times F1, because S is the one which is indicative of the difference in the speeds between this particular revolving magnetic field speed and the rotor speed. So I am going to have the rotor frequency declining as I go to higher and higher speeds of the rotor. And the moment I reach synchronous speed, there will not be any induction at all. Right? So F is equal to 0. F2 will be 0. The rotor frequency will be 0. So there is no induced EMF as well. Are you getting my point? So I should say, once it starts rotating, F2 is going to be S times F1. And E2 will also become, E2 at any omega r will also become S times E2, because frequency very much comes in the equation of induced EMF. So I am going to have this as S times E2, where E2 is the induced EMF in standstill condition. Right? Are you clear with this? So the moment the rotor starts rotating, I am going to have immediately two repercussions. One is I am going to have the frequency of the rotor circuit declining, and the second one is the overall induced EMF in the rotor circuit also declines, and both of them decline by a factor of S. And S is definitely less than 1. You guys have seen that, right? Because omega r is also in the same direction. So omega S minus omega r divided by omega S, I am going to have the slip to be very, very small. Most of the times If the induction motor is on no load, it is not loaded at all, the slip will be as meager as 1% or 2%. Nothing more than that. This one? Yeah, E2 at any other speed omega r will be equal to slip times, because the frequency has decreased. The rate of change has been what visualized by the rotor conductors, that has declined. So the frequency will decline. So the magnitude will also decline. So if this is the standstill rotor induced EMF, it will decline by a factor of S, where S is actually the slip of the induction motor. No. See, think about it. I have 2000 RPM as the revolving speed of the rotor. I have 3000 RPM as the revolving speed of the revolving magnetic field. Okay? Imagine I am a conductor sitting on the rotor. What will I see as the speed of that revolving magnetic field? That will be 1000. So the frequency will correspond to 1000. The difference. Right? Got it? So that is the reason why it will correspond to the slip. Got it? So now that I have this clear, that this is going to be S times E2, let me redraw the equivalent circuit again. I have this as R1, this as X1. I do have definitely XM, RC, and I have here the stator winding. Now I am going to have the iron core as well. This is now S times E2. It's not E2 anymore. Right? Because it is in rotating condition. I am not drawing this for stationary condition. This is going to be S times E2. I will have R2. Agreed. What will happen to X2? X2 was originally 2 pi F1 L2. Now it is 2 pi F2 L2. Because the rotor current is flowing through this leakage. Right? The rotor current is at a lower frequency. So obviously the reactance offered by the leakage flux, that will also be declining. So I have to write this as S times X2. Where X2 was the original reactance corresponding to stator frequency F1. Now X2 times S is the reactance offered by the rotor conductors corresponding to the new rotor frequency, which is S times F1, which is F2. So now I am going to have again the short circuit, no doubt. Right? Let me try to talk about some values a little bit. If originally I had applied maybe some 400 volts, arbitrarily I am saying. Let's say I have applied 400 volts and maybe I had gotten 100 volts here at standstill EMF. Right? Now maybe I have a 1500 RPM induction motor, which is omega S is 1500. Maybe omega R is something like 1490 RPM or 1485. It is easier for calculation. 1485 RPM. Right? So I am going to have the slip to be 15 divided by 1500. So that is going to be 0.01. So originally I had an induced EMF of 100 volts. Now it has become 1 volt. It's a very, very small induced EMF that I am going to get. So this will become 1 volt. And 1 volt with whatever is the resistance and leakage reactance has decreased, I agree. The current is going to be definitely very, very minimal compared to what I got during starting. That's what you would see when you start an induction motor. When you start, you will see the ammeter shooting up. The current will really go up, and as it gains speed, slowly you would see that the ammeter the pointer falls, and it comes to a minimum. Whatever is the minimum current that is needed, first of all, to develop that minimum torque, frictional torque, and also to establish the flux. Xm will require some current to establish the flux. So you will see that as the induction motor starts, the current falls very rapidly because of this particular reason. Now, this is I2. I am calling this as the rotor current. Right? Let me try to write the expression for the rotor current I2. So I can write I2 equal to SE2 divided by R2 plus JSX2. Right? I have just written the rotor impedance, as simple as that. Short circuited, so I don't have anything else. Right. Let me divide the numerator as well as denominator by S. Right? So I can write this as E2 divided by R2 by S plus JX2. Right? There is no difference mathematically. The magnitudes are the same. But it makes a world of difference electrically. Because originally I said that when the frequency of the rotor was same as that of stator frequency, I had E2 as the overall voltage. Now I have come back to the same voltage. And I said that previously the reactance was only X2. Now after the rotor has started rotating, I got SX2 as the reactance. Now I have gotten back to X2 itself. So this talks about reduced frequency current, whereas this talks as though the magnitude is the same, but the frequency is F1. It's not F2 anymore. So a simple mathematical modification of dividing the numerator and denominator by S has kind of, modified the frequency. It looks as though it has modified the frequency. In the transformer, I could connect the primary and secondary quite easily just by taking into account the turns ratio because the frequencies were the same. In this case, I could not have connected unless I convert everything back to F1. And this is the modus operandi I have adopted to convert the rotor frequency also back to stator frequency so that I can interconnect both of them. So what I am going to do now is I can write R1, X1, and of course I can write the Xm and RC, no problem. But the rotor side, I am going to write, rather than writing R2, I am going to write R2 dash by S. And then I am going to write X2 dash. Right? And then just short circuit the whole thing. And this is the induction motor equivalent circuit per phase. Nothing more than that. Right? What we have done is to convert the rotor frequencies into equivalent stator frequency. Only what we have adjusted is the resistance value. Right? And the second thing we have done is transported all the secondary side parameters to the primary side by, taking care of the turns ratio, which is not very easy to decide. I agree. In a cage induction motor, unless we have all the design parameters. But, thank you. This is X1. Right? So this is the overall equivalent circuit of the induction motor, where the resistance inherently, what was there was R2 or R2 dash if I look at it from the stator side, but I have divided that by S to take care of conversion from the rotor frequency into stator frequency. We have a little bit more of work to do on this equivalent circuit. Okay? This is R2 dash by S, right? Multiplied by I2 square. This is what is the power going into the rotor. This is the power that is going into the rotor per phase. Of course, everything we are talking about per phase. I2 is actually the current that is flowing. I2 square multiplied by R2 dash by S will be the overall power, that is I2 dash rather. I2 dash square R2 dash, right? All of these are dash. I2 dash square R2 dash by S is the power that is actually entering into the rotor. There will be definitely dissipation. That will be I2 dash square R2 dash. That will be the dissipation, right? So, whatever is the power that is getting into the rotor, part of it will be dissipated in the rotor resistance. Rest of it is the one which is converted into mechanical power. So, we are going to bifurcate this power into two portions. So, we would say out of this, I2 square R2 is going to be the rotor copper loss. And whatever we get as the difference between these two, that is I2 square R2 by S minus I2 square R2 is going to be, because otherwise where will the motor get the power to rotate from? It has to get it from here. I have got this as the total input power to the rotor, out of which I know for sure that something has been dissipated as the rotor copper loss. That is I2 square R2 within the resistance. I know physically the resistance is only R2, but I have represented that by R2 by S. So I know that I am probably supplying more amount of power than what is required by the rotor to dissipate. That more amount of power is the one which goes towards mechanical power conversion. From electrical power, now that is getting converted into mechanical power, which is enabling the motor to rotate. Right? So, I should be able to write this resistance, which I got as R2 dash by S. This R2 dash by S was the overall rotor side resistance in the equivalent circuit. This I am going to bifurcate into two portions. One is R2 dash itself, which is corresponding to the actual rotor copper loss component. So I can say R2 dash by S minus R2 dash is the one which is going to represent the mechanical power output. Of course, I have to multiply everything by I2 square. I have just eliminated I2 square because everywhere that is a common factor. That's all. So, I can draw now the equivalent circuit like this, saying that this is R1, this is X1, this is XM, this is RC. Yes. The total power that had come in was basically R2 dash by S multiplied by I2 dash square. I can write it as I2 dash square R2 dash by S or I2 square R2 by S, because power is invariant. Whether I am looking at it from the primary side or secondary side, power is invariant. It is not going to change. That's how we did the conversion also. R2 dash equal to R1 multiplied, R2 multiplied by N1 by N2 the whole square. That's what we did. Remember? So, I am inputting a power which is corresponding to I2 dash square R2 dash by S per phase. Out of that, I2 dash square R2 dash is the one which is getting dissipated in the actual rotor resistance. There is definitely more excess power. Please again think about it. Let's say 100 watts was I2 dash square R2 dash. Slip is 0.01 or 0.02. So 100 divided by 0.02 is the total power that I have given the rotor circuit. Out of which only 100 watts I have dissipated. What happens to the rest of the power? The rest of the power is the one which is going towards rotating the mechanism completely. Otherwise, where is the power coming from? So I have given 100 divided by 0.02 as the total power to the rotor, out of which 100 watts has gone dissipated. So I am going to have rest of 100 by 0.02 minus 100 as the total power that goes towards mechanical power conversion. Got it? So I am going to have basically, here I am going to divide this into two portions. One is going to be R2 dash, which is the inherent resistance of the rotor circuit converted into the second primary side. This I can write this as R2 dash into 1 minus S by S. Am I right? This is same as that. So I can write here as R2 dash into 1 minus S by S. Both these together I am having R2 dash by S. Originally I wrote it as R2 dash by S. Now both of them I have bifurcated into two different portions. That's all. And please note, this is mechanical power. So this can be a variable one depending upon how much of load I am drawing. How much of load power I am drawing, depending upon that it is going to change because the slip will change, the speed will change. If I load the motor more and more, the speed will come down, the slip will increase. So more power will be actually passed on to the rotor circuit, which will be converted into mechanical power. More power will be converted into mechanical power as well. So now I will have, of course, X2 dash. This will be X2 dash, and then I am going to complete the circuit here. And this is V1 per phase. Now I should be able to write, this is I2 dash, this is I0, which is the no load current, and this will be the summation of I2 dash plus I0, which is I1, right? That is I1, right? Is this clear? This is the overall equivalent circuit, per phase equivalent circuit of the three-phase induction motor, from which we will calculate everything for three phases by multiplying by 3. If it is star connected, we will have the line current equal to the phase current. If it is delta connected, we will have line current equal to √3 times the phase current. Whatever we are doing is per phase. Everything will be converted into three-phase line or phase quantities by multiplying by the appropriate factors. That's it. Yes. XM and RC will remain the same meaning? Yes. That will not change because I am looking at the whole thing only from the stator side. No change at all, because it is stator is still at F1. Stator is not rotating. Stator conductors are continuously looking at the frequency only as F1. Yes, because this is essentially carried by the stator winding to establish the flux initially. Right? It is the same thing like transformer. The mutual flux is established initially by the primary or whichever winding I am exciting. It's the same thing. Only thing I want you guys to recognize is that the DC machine, we had a field system separately, armature system separately. Here, I am having The field also is established by the stator side current. There is no separate current. Right? I'm not having a separate field system. And the rotor is carrying a current which is producing the torque, but that current is also coming from the stator. Where is it coming from? It is like a transformer. So if I look at the stator current will contain the magnetizing current as well as the torque producing component of rotor current. Both will be there. So I will never ever have an induction motor work in unity power factor. I will never ever have an induction motor working on leading power factor. It is an inductive effect always. I will need that current no matter what to establish the flux. And if I am establishing a flux, it is inductive. No way it can be capacitive. No way it can be resistive. So always an induction machine will work at lagging power factor only. It cannot work in leading power factor or unity power factor at any point in time. This is one of the major disadvantages of induction. We talked about all positive things. Of course, this is one of the negative things. Right? So, just to reiterate what we said, we have a rotor input which is corresponding to I2 square R2 by S, and rotor output which is corresponding to I2 square R2 multiplied by 1 minus S divided by S, and the copper loss which is corresponding to I2 square R2. Let me write it down again. So I am going to have the rotor input is to rotor output is to rotor copper loss. I'm just trying to write it in terms of ratios. So this is going to be I2 square R2 by S is to I2 square R2 by S into 1 minus S, and this is going to be I2 square R2 as such. Right? So, if I take what is the efficiency of the rotor, that is actually rotor output divided by rotor input. So, that will be 1 minus S. Right? So, I am going to have the lower the speed of the induction motor, right? The lower the speed of the induction motor, I am going to have larger and larger slip. If I have larger and larger slip, very clearly 1 minus S is going to be smaller and smaller, right? If I have the induction motor, let us say 1500 RPM is my normal synchronous speed. If it is working at 1470 RPM, 30 divided by 1500 is going to be my slip, which is actually 0.02. So if it is 0.02 is the slip, I'm going to have the efficiency to be 98%. If rather my motor works only at 1440 RPM, lower speed. Now 60 is the difference in the speed between the revolving magnetic field and the rotor speed. 60 divided by 1500 is my slip, which means that is 4%, 0.04, 6 by 15, yeah. So that is going to be 4%. If 4% is the slip, I am going to have the efficiency to be 96%. So lower the speed of the induction motor, more is going to be the losses or less is going to be the efficiency, right? So if I have a larger rotor resistance for a given current, I will have larger rotor copper losses. For a given chunk of total rotor input power, I will have larger chunk of rotor copper losses, which means I'm going to have less and less mechanical power. If I have less mechanical power, in all probability, it will be able to rotate only at a lower speed. So the slip is going to be larger. So if I look at squirrel cage induction motor, which has thick rotor bars, the resistance is small. The rotor resistance is small, the rotor copper losses would be small normally for a squirrel cage induction motor. So I can say squirrel cage induction motor, rotor resistance normally will be small. Unless I specifically make the rotor bars with some high resistance material, which is very, very unlikely. Why would I like to have lower efficiency? So, I better not make it with high resistive conductor. So, I will make it with aluminum or copper, because of which the resistance of the rotor bars are going to be small. So, I will have less rotor copper losses. So, better efficiency. Yes?
And why is the expression for the efficiency of motor, why are we considering the input for the rotor and not the input we have just lying to the stator basically, which is the...
I am currently looking at the rotor. We will definitely have to look at that as well. We will have to say I1 square R1. I am trying to differentiate between the two types of rotor. So I am specifically orienting my discussion to rotor because I want to differentiate between the two types of rotors. That's the only reason. Absolutely. I am talking only about the efficiency of the rotor, which will have at least some amount of repercussion on the overall efficiency. Right? So I am looking at only from the rotor side currently. We will look at the overall efficiency, of course. Right? On the other hand, if I look at wound rotor induction motor, I will have rotor windings. If I have to have wires going around in the form of winding, it has to be any day thinner than my rotor bars. Rotor bars are thick, whereas the wires that are going around in the wound rotor induction motor, they have to be bent, they have to be taken round and round. Here I don't do anything. I just put the bars and two end rings I put and short circuit. Nothing more than that. Whereas here I have to go round and round taking the entire winding in the form of not really lap and wave. We call this as armature winding for the AC machine. So we will have to go maybe from North Pole to South Pole to North Pole to South Pole. You have to go round and round. Go through the slots and so on. So it has to be somewhat thinner wire, otherwise I will not be able to take it round and round. So generally slip ring machines will have somewhat higher rotor resistance as compared to the cage machines, squirrel cage machines, which are of the same rating. I am talking about similar rating. Even if I compare similar ratings, if I try to look at the resistance value of a slip ring rotor's resistance versus what is the resistance of the cage rotor will normally have lower resistance, which is definitely good from efficiency viewpoint. So I would say rotor efficiency or rotor copper losses will be higher here, and so rotor efficiency will be lower. If I am talking about copper losses to be higher, see, I am bifurcating the total rotor input between two components. What are the two components? One is rotor copper loss, the other one is mechanical output. So if I increase the rotor copper loss, it goes without saying that the mechanical output has to come down. As simple as that. Let's say I am giving totally 400 watts. In the squirrel cage rotor, maybe 50 watts have gone as copper loss. Whereas in wound rotor motor, 100 watts will go as copper loss. So obviously, I will have only 300 watts left over as the output in the case of slip ring rotor, whereas in the other case it will be 350 watts. So if I assume that I am giving the same amount of rotor input to both the machines, which one will give me a better output? Mechanical? Right. Even the input depends upon R2. I agree. But out of I2 square R2 by S, how much I am dissipating as the copper loss, that determines how much is coming as the output. So if I dissipate more and more, obviously I will have only less and less left over, right? Isn't it? After removing the heat loss, exactly. So if the heat loss is larger, I will remove more. So what is left over is less. Huh? See, I am giving 400 volts. Let's say it's a 50 hertz induction motor, 10 ampere of current. Root 3 multiplied by 400 multiplied by 10 multiplied by whatever is the power factor, let's say 0.8. That is the input. That is set in stone. I can't do anything. Out of, just a second. From there, already some I1 square R1 is gone. Some core losses are gone. Let's say those are some factors, maybe some X and Y. Now what is left over is root 3 multiplied by 400 multiplied by 10 multiplied by 0.8 minus this X minus Y. That is available as rotor input no matter what. You put 10 ampere of 10 ohm of resistance, 20 ohm of resistance for the rotor or 5 ohm of resistance for the rotor. It doesn't matter. This is what is available, which is crossing the air gap and going into the rotor. That we are equating to I2 square R2 by S. That's it. That is set in stone. You got my point. It is not being generated by the rotor. The power is being given by me, not by me, three-phase supply. Three-phase supply is giving the power. Out of it, some chunk has been eaten away by rotor, stator copper loss. Some chunk has been eaten away by stator core loss. Rest of it goes towards the rotor. And I am equating that to I2 square R2 by S. It is my fictitious statement. I can write that as E2 I2 cos phi 2. Who cares? That is also true. Right? E2 I2 cos phi 2 is the one which is actually the power that is going into the rotor. The same thing will come out to be I2 square R2 by S if you actually calculate the whole thing. Right? So now, I can say that squirrel cage definitely is better in terms of efficiency because of this particular reason. So why not use squirrel cage everywhere? It's fantastic, right? Might as well use the squirrel cage everywhere. Why have another type of induction motor at all? Let me look at the starting current. What happens to the starting current? I have R1, I have X1, I do have definitely XM and RC. I have R2 dash, this is X2 dash, this is R2 dash by S. Right? This is done. What I am applying is V1. For now, let me forget about this component, although this should not be neglected. I agree it should not be neglected because I am having a good amount of reluctance in the induction motor. The current drawn under no load condition of an induction motor, which is drawn by XM and RC, is not going to be really small as transformer. Because transformer requires very minimum magnetizing current, very high permeability, very small reluctance. That's the reason why magnetizing current of the transformer is only less than 5%, less than 2% in most of the cases. Whereas in an induction motor, the magnetizing current generally is almost 25 to 30% of I rated for an induction motor. Whereas in the case of transformer, Im is only less than 5% of I rated for a transformer. This we talked about repeatedly when we were discussing transformers. Right? Look at the difference. Very clearly I can't neglect, but for the heck of it right now I am neglecting. Okay? So if I look at the current I1, if the no load current is neglected, right? I can write I1 equal to I2 dash, which I can write it as V1 divided by whatever is the resistance component plus inductance component. Right? What I have written is the overall impedance of the induction motor. R1 plus R2 dash by S is the real part of the impedance. X1 plus X2 dash is the imaginary part of the impedance. Am I right? Now, during starting, if I look at what is S, what is the value of S at starting? Omega R is 0. So, omega S minus 0 divided by omega S. It is 1. So, S is going to be 1 at starting. So, S equal to 1 at starting. So, what I am going to get is I1 or I2 dash starting is going to be V1 divided by R1 plus R2 dash plus J into X1 plus X2 dash. Am I right? That is the starting current. R2 dash is really small for a cage induction motor. Whereas R2 dash is probably not so small for a slip ring induction motor. And one more advantage I have. Slip ring induction motor, I have brought out all the terminals. I can always attach some resistance. I can attach three-phase resistance, increase the overall resistance of the rotor if I want. R2 dash is the inherent rotor resistance. I can always add an external resistance and increase the overall resistance of the induction motor to start with. Which means I will definitely get a reduction in the current. I told you that induction motors are at very high rating also. If it is a 850 kilowatt induction motor and if it is working at 11 kV or 1.1 kV or whatever, you can calculate for an 850 kilowatt induction motor what is the rated current. It will be root 3, 1.1 kV, maybe I am going to have 0.8 as the power factor at the most. So this is going to be the I rated for this induction motor, which will be of the order of thousands of amperes in all probability. Right? 1.1 into 10 power 3, of course, because it is 1.1 kV I said. So I am going to have maybe some thousands of amperes of current. Starting current will be 6 to 8 times normally. So I am going to draw 8,000 amperes of current. The power system authorities will come and disconnect my power supply immediately. So including a rotor resistance in the induction motor external to the rotor circuit is possible only in slip ring rotor induction motor. It cannot be done in the case of a squirrel cage induction motor. This, including a resistance, will help me actually improve the starting performance at least by reducing the current. So, I will not be able to start an induction motor which is rated for extremely large values without including a rotor resistance or without including any other starting means. Right? I have to include some kind of starting technique in my induction motor. Actually, the power system authorities generally put up a rule. It is there in India also. People flout the rule here and there. But if an induction motor is rated for more than 50 kilowatt, you cannot start it directly without including any other starting methods. If you try to start an induction motor beyond 50 kilowatt capacity directly by connecting it to the three-phase supply, you can be penalized. This rule is there because the induction motors take heavy starting current. You will see a dip in the voltage. Normally, you will see like a welding equipment, if you connect directly to the supply, you will see all the lights going very low. The same thing you can observe if you are starting a very large capacity induction motor, because the voltages will really sink. It will become very low. Normally for a short while until the machine gets started. That's the reason, right? So, slip ring induction motor comes in really handy when you want to tamper and somewhat modify the characteristics of the induction motor. So that leads us to the discussion on slip speed or slip torque characteristics or speed torque characteristics. So let us try to first of all, just like how we saw for the DC machine, speed torque characteristics, let us try to take a look at the speed torque characteristics of the induction motor. Okay? So we said that 3I2 square R2 by S into 1 minus S. Please see the 3. Never forget the 3 when you are doing the induction motor problems, right? We do everything per phase, multiply by 3. So this is going to be the mechanical output, right? That has to be clearly equal to TE multiplied by omega R. What is the torque that is generated multiplied by the speed of the induction motor? Now we also said omega S minus omega R divided by omega S is slip. So I can write always from here S times omega S equal to omega S minus omega R. Right? Which means I can say omega R equal to 1 minus S times omega S. Right? So, let me put this here, this omega R, let me try to substitute here. So, from which I can write TE equal to 3I2 square R2 into 1 minus S by S omega R. Which I can again write it as 3I2 square R2 1 minus S. Here I can write this as 1 minus S times omega S. Am I right? Okay. So I can happily cancel these two. So this expression is a very important expression in induction motor. Omega S, this S is subscript, okay, synchronous speed. So this gives me the expression for torque. So this will be the torque in Newton meters. What I get here will be the torque in Newton meters. Now we just neglected the parallel component of current or the no load current. Let me do the same thing. What we wrote as I2, we wrote it here, right? This is what was our I2, right? In starting we neglected S equal to 1, so we just removed that. Otherwise I have to include that as well. So this is my current. Actually I should have rounded this expression. This is what is actually my expression for the current. Let me substitute that here. first of all, what is I2? I2 or I2 dash, whatever. That is going to be V1 divided by R1 plus R2 dash by S plus J into X1 plus X2 dash. From which I can write I2 dash square is equal to V1 square divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square. Right? Just substitute that in the torque expression. Right? So I get TE equal to 3V1 square divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square, and then I have R2 dash divided by S omega S. That is the expression for torque when I neglect the no load current. When I neglect the no load current, this is the expression for torque, which is again a pretty important expression in an induction motor. This is one of the most important expressions. So there are some important expressions. One of them is here, the other one is here. So these two are quite important as far as the induction motor is concerned. Yeah. I2 is the rotor current. I2 dash is the rotor current visualized from the stator side, neglecting the no load current. Please look at this. We have neglected this. This is the no load current. I just said forget about the no load current. This is I2, right? I2 dash rather. So I will get I1 equal to I2 dash if I neglect the no load current. Is this clear? So, yeah. See, the thing is that I told you that power is invariant. I2 square R2 will be equal to I2 dash square R2 dash. So I replace R2 also by R2 dash. So I don't think there is any mistake. Is that fine? Okay?